Good morning, everybody. This is Alessandro Iafrati from the Institute of Marine Engineering in Italy, and I am presenting the activities done by the Specialist Committee on Modeling of Environmental Conditions. I want to acknowledge the important contributions by the other members of the committee, which are Jules Scharke, who acted as secretary, Martin Deviecki, Toshifumi Fujiwara, Yu Jong Kim, Pedro Mello, Yushang Ma, Solomon Im, and Xinshu Zhang. Some of us had the chance to meet already at the during the kickoff meeting just after the end of the 28th ITTC conference in Bushi. Then we had afterwards physical meetings in Rome, Tokyo, and Gdansk, as well as one rather short meeting during the OMI conference in June 2019. Of course, due to the pandemic related to the COVID-19, the last meeting was done virtually. The committee addressed the assigned terms of references, and I will present first some key points on modeling of the stream environment, on breaking waves, and then wind and wave interaction and its effects on the extreme wave generation, wave current interaction, and consequences of the breaking occurrence. Hence, I will go briefly through the three guidelines on waves, winds, and currents. So, the first problem we have when we need to reproduce the stream environment in the laboratory concerns the characterization of it. So this is strongly affected by the variability of the data because of the limited number of observations and of the length and domain extension of the observed area. By using higher order nonlinear simulation, it was demonstrated that space-time series are less sensitive to sampling variability, and furthermore, the dimension of the area relative to the wavelength and the period are more important than the sampling ratio. The occurrence of crossing seas is another important aspect that has to be accounted for, as it enlarges the instability region, or in other words, augment the possibility, the probability of exceedance. In this respect, the higher order effects are also very significant and have to be considered. By using a suitable experimental setup, it was also shown that it is not just the crossing angle that matter, but also the directional spreading may have a role on the exceedance probability. For a given crossing angle, for instance, it has been shown that the narrower spreading leads to kurtosis and wave height exceedance probability much higher. The experiments are very difficult and expensive, the high order spectral method, AHOS method, are often employed as a very valid alternative, although a rigorous validation and verification of the limits of those approaches is always necessary. One of the problems in this case concerned the initialization of the numerical simulation. As expected, the results show that the linear approach works well for small steepness, but for higher steepness, higher order approach are strongly needed, but then very accurate reproduction can be achieved in this way. The problem becomes even more complicated if you want to reproduce freak or raw wave, if you like. However, there have been some recent advances in the field which result to be very precise. The approaches may be profitably make use of the data simulation of real measurements, and then by numerical method, one can tune the different components to reach the desired profile. Data simulation system based on stereo camera systems are becoming more and more popular. The great advantage is that they may be used both on fixed platforms, but also on board of ships, even though, of course, in these cases, the ship motion has to be accounted for and compensated during the post-processing of the data. Among the different ways to initialize the high-order simulation, there is the Monte Carlo approach used in combination with to combine the different components of the wave and then to initialize the simulation. In this way, a rather precise reproduction of the desired time history can be achieved, as it can be seen here. Even though the numerical model helps in testing the initial condition to be used, when we take these initial condition and want to use them to drive the wavemaker, we have to be very careful in order to avoid that some spurious component appear. There have been some recent advances in developing control techniques that are able to apply a nonlinear control and nonlinear correction to the wavemaker system. The braking is also another important issue of the modeling of the environmental condition. And in spite of its relevance for the loading on and for the wave dynamics, the braking remains still a rather complex phenomenon, which is hard to predict and to be described as well. Even though there have been significant advances in the development of multi-phase Navier-Stokes models, there are still some limitations, partly due to limits in the numerical model, but also there are some limits in the reproduction of the exact experimental conditions. Aside from that, however, there are closer and closer agreement between the numerical and detailed PIV measurements in terms of kinematic and typology of the braking event. And this means that the computational fluid dynamics is becoming a tool to investigate deeper this phenomenon. Aside from the rotational flow taking place inside the braking region and of the consequences in terms of loading when the braking region impacts on a floating or fixed structure, the braking introduces an upper limit to the steepness, and furthermore, it dumps the higher harmonics in the spectrum. So the lower harmonics remain rather unaffected by the braking occurrence. In the case of modulation instability developing on narrow spectra with sideband perturbation, the occurrence of the braking frozen the energy transfer from the upper to the central components to the lower sideband. The braking ceases afterwards due to the combined effects of the reduction of the wave amplitude because of the dissipation and of the frequency shift. Both effects indeed contribute to the reduction of the steepness. Something similar has been also observed in when the braking occurs as a result of crossing wave group, in which the energy loss mainly comes from the high frequency components. A very detailed overview of the state-of-the-art knowledge on the braking of surface wave was provided by Babanin in 2009, who analyzed in depth the onset of braking, its probability and occurrence, and he analyzed a very wide set of laboratory and field data in various conditions. It was found that in some cases, the wave steepness can exceed the Stokes limits that is usually known for stationary waves. Let's move now to the wind-wave interaction and its effect in the generation of stream waves. Of course, the open ocean is exposed to wind, and that induced loads on the upper part of the structure, but it also interacts with the wave field and contributes to the development of extreme events. When performing experiments, it is not always possible to reproduce the actual wind condition, and thus wind load can be estimated by computational fluid dynamics tools. Some recent results show that such an alternative approach is rather reliable even for complicated topsides. When reproducing the wind, it is important to take care of the wind profile and of the turbulence. In this regard, some models have been developed based on recent hurricane data. In some conditions, it is not possible to reproduce the wind, but nonetheless, it is important to apply the wind-induced loads. Some examples of wind-induced wind load simulators are shown over here, and they can be used in model testing. And in particular, they're adaptable, and they can be easily adapted to the speed of the speed of the ship and to the drift and heeling angles. Of course, the wind may affect the wave dynamics and may also trigger the breaking occurrence. Of course, the situation is completely different in open sea and in the basin because of the different fetch. Some recent experimental studies have highlighted some of the changes induced by the wind on the wave profile. Through the numerical investigation, it was found that not necessarily the wind anticipates the breaking. Even if the wind is blowing on the back of the wave, what happens is that in some cases, in particular in the modulation and stability case, the wind reduces the growth rate of the stability, and then the breaking is postponed. However, the wave in this way reaches a higher steepness, and when the breaking occurs, it is much stronger than without wind. Such findings were consistent with some laboratory experiments done by Teboul and Karif in 2008 and 2006. The wind is generally non-uniform. A correct characterization of the spectrum and of the gas factor is essential. Recent analysis of the field data show that the gas factor decreases and the turbulent intensity increases with the gas duration. As for the waves, a probabilistic approach also exists for tropical cyclones. Long-term field measurements are available, and some comparison between wave height obtained under synthetic cyclone and historical cyclones are available. In open ocean, also current exists and may have an influence on the waves. There are several models that, based on the meteorocean conditions, provide estimates for the loads. One of them is the NORSOC N003. Generally, these models are supposed to be conservative and then useful for the design. However, at least for this model, some comparison with the hindcast data for waves and currents have been performed, and it has been found that a very satisfactory agreement was found. However, looking at the comparison was so good that it indicates that this model is not always conservative as it was supposed to be, and then we should be very careful when using it, considering that we should introduce some additional corrective factor. The current may have significant effects also on the development of raw waves. In some experimental conditions, the probability of occurrence of the raw wave can be increased up to an order of magnitude in a flume. in some wave-based tests, it has been found that the increase in the probability of occurrence can be even higher than this. Some specific studies have been also done in order to investigate separately which is the effect of the shear and of the use of the cuneiform current on the development, on the modulation and stability of a peregrine breeder. These studies have been done by using a modified Schrödinger equation. Based on the results, it can be seen, as you can see from these pictures, that there is an increase of the growth rate in presence of positive shear and opposite currents, and whereas there is a reduction, a corresponding reduction of the growth rate in presence of negative shear and of a favorable current. Similar studies have been also conducted experimentally, and it was found that the current may trigger the instability in cases in which it would haven't developed without the current. Let's now have a look to at the most significant points highlighted in the 3 guidelines that we have developed. The guidelines of wave was already developed at the previous ITTC conference, presented at the last ITTC conference, but during this term it was substantially improved and enlarged in contents. For these guidelines, we focused on linear regular waves, nonlinear effects, analysis and control, wave frequency, low frequency reflections, radiation or reflection from the model and from beaches and sidewalls, deviation from the ideal conditions. Then we analyzed also the aspects of irregular waves, starting from wave spectra, nonlinear effects, analysis and control, bimodal and multimodal spectra, and geographically consistent of the spectral selection. For most of the irregular wave applications, the averaged wave height and periods are the most significant quantities to be considered. Such quantities should be constant in space and time. The selection of time history for the testing should be based on some criteria. Of course, it has to assure the minimum variation, the minimum transit effect in the model tested up, the minimum reflection from the beaches, and from sidewall and sidewall of the tank. And also they have to assure at least a minimum of 10 cycles, 10 wave cycles. The analysis can be done in terms of time domain, then using zero crossing techniques, the crest and trough analysis statistics, the root mean square, and the root mean square of time series. The analysis can also be done in the frequency domain by using the Fourier transform or the statistics of the different harmonics. Nonlinear aspects are mainly associated with the steepness. Of course, the wave steepness, which is usually defined as Ka, defined how much the wave system deviates from the linear one. Of course, the higher is the nonlinearity, the more asymmetrical is the wave profile. The literature is full of studies where the nonlinear effects are examined, and in the guideline we have provided some of the key ones, and some of them are listed here. Second order approaches, second or higher order approaches have been studied in the past, starting from the Stokes suspension, high order spectral model, and nonlinear Fourier analysis. The instability associated to the nonlinear effects in steep waves have been, for instance, analyzed by Toffoli and Typhoon and Fedele. Nonlinear generation method to suppress the unintended second-order free waves were proposed by Schaffer in 93 and 97. Nonlinear effects on the wave-height distributions are discussed by Tefun and Fedeli. And the study on a specific study aimed at understanding how the raw wave can be generated by bounded harmonics was presented by Fedeli in 2016. The high-order spectral method is usually used to study the wave field transformation and wave propagation at different orders, and the specific wave modeling methods have been developed for shallow, intermediate, and deep water by using the nonlinear Fourier analysis. Of course, in a finite basin, there are some additional effects on the wave field. First of all, the finite depth of the tank change the dispersion relation, and any uneven bottom induce reflection and spatial variation. The resultant depth also increases the nonlinear wave-wave interaction. A significant reduction of the effect of the sidewall can be obtained by passive or active absorption system. Something similar holds for the parabolic beaches located at the end of the tank. Some apparently minor elements may still play a role, and these are, for instance, the corners induced by in the shape of the basin or in any system that is inside of the tank. This is, for instance, so special attention is needed for the waveboard to be smooth further movement across the corners, the waveboard movement optimization to suppress the spatial perturbation of the wave field, and waveboard with continuous soft curved geometries. When installing a new damping system, it is important to check and to measure its performances and to characterize the absorption coefficient. Several techniques have been proposed to distinguish the incoming and reflected wave, and then to account for the Doppler shift in case of moving probes. And then the information about the damping features of the damping system is fundamental to decide the length, the maximum length of the test duration in the tank. Of course, the waves interact with the wave generator and with the sidewall and model. Transverse and standing wave can be generated, particularly present on single board wave makers without straighteners. Passive, or even better, active absorber are advisable not only to suppress the transverse standing wave, but also to reduce the time between two successive tests. It is necessary in any preparation of the model to define a test interval between two different repeats of the test of the experiment. And solution to avoid or to suppress the long-standing wave were described by Van Essen in 2014 and 2016. When arranging our experimental setup, it's also important to remind that there are deviations from the ideal condition. Any deviation should be possibly avoided, or at least its effect on the measurement to be reduced as much as possible. Also, it is important to evaluate carefully which are the consequences in terms of the test and of the test results. It is worth remarking also that when reducing the scale, the waves are keener to develop modulation instability. Partly, the phenomenon is reduced by the stronger viscosity and surface tension effects, but a check of the accuracy and repeatability of the wave quality is essential. Of course, irregular waves are more common in open oceans. There are several aspects generally employed to model them. In this case, the duration of the experiment is really fundamental. Typically, it is 1 hour for seakeeping and 3 hours for offshore engineering applications. Of course, particularly for large steepnesses, nonlinear effects matter. Several techniques have been developed to calibrate a wave system. It is important to avoid from the very beginning the generation of spurious component, and in this respect, the nonlinear control of the wave maker is fundamental and very advisable. Often the spectra is the spectrum can be either bimodal or multimodal. And this happens when one or more swells occur and are superimposed to a local wind sea. Several models exist, and for instance, Sochi-Huble or Torsetaugen. However, I would not. We didn't discuss these aspects too deep in this guideline, as there is a more specific guideline that was developed during the previous term, and the details are given up here. When selecting the spectrum for the wave, it is important to account for some specific features of the place where the structure has to operate. Typically, in some specific areas, there are swells coming from one side, the wind speed and a local wind sea superimposed to that. But in some region, there are not just one swell, but there are maybe two swells, and then all the spectrum has to be considered. The spectrum can be also seasonal dependence, and some specific studies for some areas have been developed, and they are referenced in the guideline and can be used for, I mean, if necessary, for those regions. Then we developed from as a new guideline, the guideline on laboratory modeling of wind. We considered steady wind, spectra, turbulence, gusting, squalls, vertical and horizontal variation, geographically consistency, interaction with waves, generation techniques, and measurement techniques. Generally, wind fluctuations are faster than the ship and the offshore structure motion. This means that the steady wind is more relevant to assess the response of the water. Usually, the average wind speed is taken over 1 hour, and it is conventionally measured 10 meters above the water level. For considering the most critical conditions that have to be reproduced, a mean wind speed corresponding to 100 year return period has to be considered for the design. Well, frequency excitation is also important for the specific application and for the design. This is the case, for instance, for station keeping tests of ocean platform. Then in these cases, the wind spectrum has to be applied. The wind gusting is usually assumed to be a Gaussian stochastic process, which can be fully described by a wind spectrum. There are several spectrum models the most common are the one by the API and by the NPD, Norwegian Petroleum Directorate. They are provided here in the guideline. The turbulence level in the wind is about 0.1 and between 0.1 and 0.2. And in order to reproduce such a variation, the multi-fan control and multi-fan systems should be employed preferably, because they are very flexible, and they by activating and deactivating the different fans, we can reach the desired variation, either vertical or also in terms of the turbulence. The gusting is another important phenomenon to be accounted for, in some cases at least. And as discussed, it's fully Gaussian, is assumed to be a Gaussian stochastic process. And the spectrum, however, can depend on the wave age. There are some examples of parameterization. Some references are provided in the guideline. However, there are no widely accepted version for the elevation and for the gas factor to be used for engineering purposes. The fluctuating wind velocities can be reproduced by the wind generator, and in this sense, the multi-fan generator system can be very useful. In the region of maximum and minimum wind velocity, it is important to check that the Reynolds effect of the wind can be ignored. The square represents a strong transient wind generation generated by a convective storm. And also in this case, there are no widely accepted parameterization. Some expression of the gas factor for squall winds are provided in the guideline, though. Very limited full-scale data for the wind profile are available. It is clear, however, that the wind profile, the vertical wind profile, is developed by the sea surface roughness. There are some power law given by the API that seems well accepted by the community. When using wind blowers in the basin, it is necessary to cover the entire model. Also taking into account the possibility that the model moves during the test and exit from the wind area. However, if we are interested in testing, for instance, wind farms, in this case, the area in full scale is several kilometers, and then the wind field should be reproduced taking into account the horizontal variation in such a large area. This means that we may also have transverse variation of the wind. Controlling the wind in the transverse direction is not so easy, and the only way to enforce large horizontal variation is to, or control the horizontal variation is to employ multiple wind generator system in different position and different part of the tank. As for the wave, also for the wind, it is essential that the wind conditions are reproduced according to those found in the specific area of installation. Some examples of the specific phenomena occurring in some areas are provided in the guidelines and have to be taken into account wherever it is possible. In heavy sea conditions, the interaction between waves and wind cannot be neglected. There are several laboratory studies that show how the wind and the velocity profile in the air side change because of the presence of the waves. And something similar can happen in the model test during the model testing, even though it may strongly depend on the fetch. So the fetch is usually too short to have significant change in the wave profile, but still the wind velocity can be changed because of the presence of the wave. In order to generate the wind in the laboratory, generally propeller or Sirocco wind generator are used. The wind blowing area has to be at least twice the model length. The higher is the number of fans, the higher is the possibility to reproduce the turbulence and the horizontal and vertical variations of the wind. Most commonly, the wind load is calibrated rather than the wind velocity, would not obey to the full scaling. In some cases, during the calibration, it may happen that the changes in the projection area are necessary to compensate the different Reynolds number. Even though the wind is generally the wind fan, it's generally assumed to be most realistic as it includes the dynamic of the wind effects of the flow on the flooding structure, and in particular the change of the wind force due to change in the heating and the lift effect and so on. In some cases, the wind load can be directly applied by a wire winch setup. The good point of the wind winch setup is that It provides a constancy of the applied load with hidden changes, and more important, the applied load is well known because it is measured together with the model test, whereas the load induced by the wind is difficult to be measured. Finally, for the measurements, usually the pitot probes, hot wire anemometers are usually employed, it is important to remark that at model scale, the accuracy, the precision of the tool has to be much higher than at full scale. Depending on the application, the calibration type, which means wind load one. So for the calibration of the either wind load, one or more sensors may be required in the testing area. Then we delivered also a new new guideline on the laboratory modeling on currents. In this case, we discussed the interaction with waves, the generation technique, the vertical and horizontal variation, the turbulence and oscillatory currents, and the measurement techniques. The current, as already discussed, may affect the development of the growth rate of the modulation instability, and in some cases they may trigger the instability. Currents in basin are usually generated by recirculating water either in the basin or outside. The turbulent intensity in the measuring area should be less than 5%. In order to reach such low values of the turbulence, specific structures like perforated walls or grids or straighteners can be employed. The vertical profile is obtained by a proper control of the pumps at different layers, or by inserting perforated walls with different void fraction at the different layers. The horizontal variation of the currents is more difficult to be achieved, and the only way is to use a variable depth. By varying the height of the bottom, we can change. We can either we can increase the current speed. We have to, when positioning the structure, we have to consider that the turbulence level can vary because of with the distance from the wave entrance, and then such a variation has to be accounted for. When necessary, for instance, in the case of tropical storm, when we want to reproduce the typical condition of tropical storms, then flow condition, oscillatory flow conditions can be reproduced in laboratory, and these are some examples of application. For the measurements of currents, usually all the tools that are commonly used for hydrodynamics can be employed, and they are the particle image velocimetry, stereo PIV, laser Doppler velocimetry, or particle tracking velocimetry, holography, and any other methods, and some of them are reviewed in the ITTC 2014. The acoustic Doppler velocimetry and the ADB profiler are widely used for measurement in non-uniform flows. So, concluding, the activities of the present committee finishes here. We do recommend the adoption to the ITTC committee, the ITTC, to adopt the 3 guidelines on waves, wind, and currents that have been proposed. We would be happy to answer any question raised by the audience. Thank you.